Hello, welcome back to PhysioDesigner tutorial series. In this tutorial series, we are going to create a model of human upright posture control on PhysioDesigner. In this time, we modify the Model 1 that we created in the previous tutorial and introduce a time-delayed feedback. Let's begin. We were considering the control mechanism of the human quiet standing posture by modeling the human body with an inverted pendulum. Important variables and parameters in the model are shown here. The tilt angle is theta, height to the center of mass is 1 meter, and weight is 60 kilograms. The gravity is 9.81 meter per second square, and T is the ankle torque. Do you remember that there are 5 types of the torques forming the ankle torque? 2 of them are related to the intrinsic mechanical impedance with passive stiffness and viscosity. Their other 2 are active neural feedbacks determined by delay tilt angle and angular velocity. The last one is noise torque. In the second model, we introduce the time delay for the active neural feedback torque. Firstly, the parameter values, K and B, for the intrinsic impedance are the same with those in the Model 1. Then, we consider 0.2 second, that is 200 millisecond, time delay for the neural feedback. The time delay includes the transmission time of the sensory information from the sensory receptor to brain, and transmission time of the motor control signal from brain down to muscle, and latency of force generation. The values of parameters P and E are the same with those of the Model 1, but theta and theta dot with time delay refer the values of delta time ago. And we do not consider noise torque in this model again. Now, let's create the Model 2. At first, load the Model 1, which we created in the previous tutorial. What we need to do is to introduce the time delay for theta and theta dot. W is used to represent theta dot in this model. Open the Physical Quantity dialog, right-click the module, and select Edit Physical Quantity. Selecting theta in the upper table, set the max delay value in the Basic Setting tab. Now let's set 0.3 here. This value is important to consider the time delay of theta. During simulation, to access to a past value of theta, the simulator must keep the past values of theta in memory. The max delay in this dialog is used to define the maximum length of the array to keep the past values. Similarly, for W, we need to set the max delay. Then in the definition of the active neural feedback terms, FP and FD, we use delay function. Let's search FP and FD in the table. There is search function. So input only F in the text box, and click the loop icon to search. Then the items matched to the keyword come to top of the table with blue color. Select FP, which is now on the top of the table, and go to the Implementation tab. To refer the past value of a variable, use delay function, which takes 2 arguments. The first argument is the variable name, and the second argument is the delay time. In this case, set del to second. Similarly for W. A parameter delta is added at the bottom of the table. This is of a static parameter type, and let's set 0.2 second, which is within the maximum delay. That's all. This time, modification is quite simple. Close the dialog, and let's save the model as Model 2. Now let's observe the dynamics. Call Flint from the menu. Click Run button to start a simulation. As the parameter values set in the model, all parameter values are the same with the Model 1, except time delay delta. In the case of the Model 1, the value converged to the fixed point, but in this case, it shows oscillatory profile on converging process. On the theta W phase plane, the orbit makes loops near the fixed point. Let's see what happens if we use a little bit larger time delay. It converges, but the oscillatory behavior was enhanced. Okay then, what if we use even larger time delay? You see, theta diverged. This is so-called delay-induced instability. Because of the time delay, the neural feedback proportional to theta, whose gain is p, becomes 0 after the state overran the upright posture. Then the system tries to draw back the state to the upright posture, but again the state overruns. When the value of p is large, with respect to the delay, the amount of the overrun becomes larger and larger each time the state overruns the upright posture, and finally falls down. Considering this point, let's use a little bit smaller value for p this time. It is still making oscillation, but converging to the fixed point, that is to the upright posture. This is because we used smaller p. The response speed is slower with respect to the amount of the time delay, and the amount of the overrun did not accumulated. This is rather intuitive explanation of the phenomena. We can examine the stability based on mathematical analysis. To analyze the stability of the upright posture of the inverted pendulum, usually we examine the sign of the eigenvalues of the system. However, there are delayed feedback terms, which refer the past values. It is not simple to derive eigenvalues. Firstly, we need to linearize the terms with time delay. Considering the first-order Taylor series expansion with respect to delta, rewrite the terms as shown in the slide. Then the system can be rewritten as indicated by the arrow. On this ordinary differential equation, we can calculate the eigenvalues, considering the characteristic equation of the system, where lambda represents an eigenvalue. Finally, eigenvalues can be written like the top equation in the slide. The condition to obtain asymptotic stability of the upright posture is that both eigenvalues, or real part of the eigenvalues, are negative. Let's consider this inequality for lambda plus. Then we can derive three conditions. If those three conditions are satisfied, the upright posture is asymptotic stable. As we already saw in the simulations, when we increased the value of time delay delta, the third condition was broken, and the system lost the stability. But then we decreased the value of p, again the system converged to the upright posture, because the third condition was satisfied again. That's all for this tutorial. In the next tutorial, we will introduce the new control scheme. Thank you for watching. Hope to see you next time. Bye-bye.